Hi everyone. So this is just going to be a short video covering what we need to cover today, which is Patriots Day. So we'll talk really briefly about percent dissociation, how to calculate that, and how to use it from data from an ICE table to calculate this. And then we'll talk a little bit about polyprotic acids, and then we'll finish off talking about the relationship between Ka, Kb, and Kw. So why don't we get started? So percent dissociation is pretty straightforward. When we look at the equation, right, where it's basically a ratio comparing how much acid did I start with, so that's the protonated acid, and then how much has dissociated, right? And so this is going to be affected by Le Chatelier's principle. It's actually at lower concentration. So if we look down here, we're looking at the concentration of acetic acid. So at low concentrations, you actually get about 4% dissociation, but as that concentration starts going up, and then based on its Ka, it's actually going to dissociate less and less and less, and then kind of asymptotes around 0.42% dissociation, right? So we're seeing weak acids, right? When we're talking about partial dissociation, strong acids are close to 100%. Weak acids are below 10%. And like I was saying before, acetic acid, around 4% dissociation. So how do we use this equation given like a real life example? So I'm going to go through this fairly quick. We're pretty good at ICE tables now, so it's got a lot of it's going to end up being a lot of the same processes. So it's asking us to calculate the pH and percent dissociation for a solution of 0.033 molar hydrofluoric acid. And so we have the balanced chemical equation of hydrofluoric acid reacting with water. And we're also given the Ka for this reaction. So we can set up our ICE table so we know what concentration of HF we started with, right? Things should be looking pretty familiar here. So we fill in our ICE table. We can use our Ka expression of products over reactants. We can plug in our value for Ka as well as all our values from our E row. So we have our products are X, the concentration, and then the concentration of our reactants, HF, is 0.033 minus X. And again, we're going to practice using our assumptions. So if we were going to write this as an assumption, I would write down assume X is much, much less. Well, it needs to be compared to something, and that's what I'm looking here. It has to be a lot less than 0.033. If that's the case, effectively, that's saying that X is so small, I can make a reasonable approximation that my fraction looks like this. If that is the case, it's a lot easier to solve for. It becomes a very simple, straightforward math problem, and we can solve for X. We need to double check our assumption, and that's what we have here. So 0.033 minus what X is actually 0.030. So I wanted to include an example where actually our assumption failed. Right? Our rule is that when we check the assumption, it needs to hold up to the same amount of sig figs. So if we only had one sig fig, so let's say like 0.03, we'd be in good shape and it would say our assumption held. But we actually have enough significant figures that we see we're saying we're making an assumption that basically the concentration doesn't change. But when we do solve for X, we find out that X is actually incorrect. It is giving us the wrong conclusion. So our assumption has failed. That gives us only one other option, and that is going to be using the quadratic equation. So I can't use my assumption, so I have down on the denominator still 0.033 minus X. Set it up in quadratic form, plug it into the quadratic equation, and then we get two values for X. One is negative, one is positive. So we're going to use the positive value. So now we have our value for X. So we can actually see it's different than our assumption. Before we had 0.0, I forget what the number was now. We can go back for a second, right? Our assumption, when we're using, based on our assumption, it's actually 0.0034, what it really should be when we're seeing 0.0033. So it's a small change, but it's enough that makes our assumption fail. So now that we've solved for X, we can plug everything in. So I see that my concentration for, well, X, what does it represent? It's the concentration of hydronium and also the concentration of fluoride, and that's what I see there. And I also can calculate the concentration of my protonated acid, HF, and I got that done. So the last thing it was asking us to do was calculate percent dissociation. So again, we pull up our equation. It's how much I initially started with, and then how much dissociated. So the equation I have written there is actually the one from the book. What I think is a little more intuitive, it's going to be the same equation. I was going to write it a little bit different. Why not write it like this? It's the amount of conjugate base final over how much HA I started with. That might be another easier way to see it, rather than having it saying like HA dissociated. Well, the amount of HA that dissociated is going to be equal to the amount of either hydronium or to the conjugate base, F minus in this case. So we can plug in our values. So if we take a look here, there is how much I started with. Here's how much dissociated. Do that out, multiply it by 100%, and I find out that HF, under these conditions, is only 10% dissociated. So it's still a lot less than that 100% of a strong acid. All right, so that covers talking about percent dissociation. This kind of just almost gets tacked on at the end. Everything that we've been looking at so far in terms of weak acids has been monoprotic acid. And so what monoprotic, if we write down that word, monoprotic, mono meaning one, protic meaning acidic hydrogen, and that's something when we have the generic form of HA. It's an acid with only one acidic proton, right? So if I gave you an example, like say acetic acid, right? So if I draw the structure of acetic acid, right, one point I want to point out is that even though there are 4 hydrogens in the structure, only one is acidic. So that would still make it monoprotic. However, there are compounds that have more than one acidic proton, and we're going to call them polyprotic acid. Poly being many, protic again being acidic hydrogens. So what I have below in the table is a series of polyprotic acids. And what we notice right off the bat is actually there's several acid dissociation constants, Ka1, Ka2, and then in the case of phosphoric acid, a Ka3. So what that is telling me, let me just pick an example. Let's say we do sulfuric acid, right? I'll take an example like that. So we have H2SO4. There's my sulfuric acid. It reacts with water, and it's a strong acid. So let's say 100% dissociated. And I've mentioned that before, right? The Ka is very large. So we're talking over 1 million. But technically there's a Ka value for this. And if I write out predicting my products, 1 proton gets transferred to the water to become hydronium. That will leave behind SO4 minus and hydronium. We'll have 1 Ka that describes that reaction. So I'll call that 1. However, this structure here, and this is something I would need to let you know, but that hydrogen there, this is still an acidic hydrogen. Again, we're going to get to the end of the chapter and be able to predict which are acidic. For now, I need to tell you. So we've gone from H2SO4 to HSO4. We're saying that HSO4 is that proton, that H is still an acidic proton. Remember, this is floating around in a large amount of water. So you're going to find another new molecule of water that this HSO4 minus can interact with. It's a weak acid, right? So I'm going to draw it as an equilibrium arrow, but I can still transfer that H to a hydronium. That will leave behind sulfate and make an additional hydronium. So it's actually a 2-step process. And if it was something like phosphoric acid, there'd be even a 3rd step. So it sounds like this could throw a wrench into solving for the pH of a polyprotic acid, but we're going to find out there's one simple thing that can help us. As long as we're not doing very, very, very sensitive work, we can make a very reasonable assumption. So let's take a look at, say, something like carbonic acid. Let's compare the magnitude of Ka1 and Ka2. So don't really worry about the number in front. I'm more cared about the order of magnitude. So we see Ka1 has a Ka on the order of magnitude of 10 to the negative 7. And Ka2 is on the order of magnitude of 10 to the negative 11th. That's a change in 4 orders of magnitude. That means Ka2 is 10,000 times weaker than Ka1. And what you can do is you can start to go through comparing Ka1 to Ka2, and you'll see there's these very large changes in order of magnitude comparing how large Ka1 is to Ka2. In general, we'll make a very reasonable assumption, and this one we don't check. We just are going to say it's our assumption. As long as you're having several orders of magnitude difference, Ka1 is much, much greater than Ka2. In that sense, even if you have a polyprotic acid and you need to determine the pH of a solution, imagine you have like phosphoric acid and you have a 0.1 molar solution. If I give you the Ka1 and Ka2, predict the pH of that solution. It's actually not that bad. We don't need to do 2 ice tables. We will make the reasonable assumption that we only need to do 1 ice table and only use Ka1 because the vast majority of hydronium that's formed is coming from Ka1. That is going to affect the pH. Yes, Ka2 does affect the pH, but it's so small, right? We're going to just make the reasonable assumption that in the end, it doesn't affect the pH, the final pH. And I've actually gone through myself and done it out by hand with 2 ice tables and proven to myself that within significant figures, Ka2 does not affect the pH. So why don't we put that into practice? So what I have here is carbonic acid. So it's a polyprotic acid interacting with water. We've already said Ka1 is going to be much larger than Ka2. So all I need to do is worry about Ka1. This is the second step, right? I could theoretically write out a Ka2, and then we can see here clearly, again, that huge change, that 4 orders of magnitude difference. So we are only going to concern ourselves with Ka1. So take that Ka, and then all we need to do is finish off the problem. Now I've asked you to find the pH, and I've given you the concentration to start with of carbonic acid, and I give you Ka1, and kind of becomes a lot of the same steps again. Set up my ice table, take Ka1, write out the expression, substitute in my variables. I can try making my assumption again. We get a value for x. It's a lot quicker than using the quadratic equation. We check our assumption, and it actually is going to hold this time. So I don't have, let me go back just a little bit. We can double check. So if I assumption, right, we said assume x, and in this case, be much, much less than, and what am I comparing it to? 0.020. So if I set up my check, 0.020 minus, right, 0. And I'm gonna subtract this number to see if it affects that concentration overall. 1,2,3,4,9,3. Plug that into my calculator, which I do not have. Let me do it real quick on my phone. So if we take our 0.02 minus 0.000093, I get 0.019907. I check my significant figures. Remember, subtraction, it only matters how many decimal places, the number that has the least amount of decimal places dictate what my final answer will be. I take a look at 9 is going to round that 9 up, and it becomes 0.020. My assumption holds. So we've solved for x without any need for using the quadratic equation. X we recognize is also the concentration of hydronium. Dump it into our pH equation. we get a pH of 4.03. It's nice with acids and bases. You can always check your answer, maybe not the numeric answer, but does it make sense? 4 is less than 7. It's a weak acid. That makes sense to me. pH is less than 7 are acidic. It's not like a pH of 1 or 0, which would indicate a strong acid. pH of 4, indicating weak. We've pretty much checked off our boxes. Maybe we might have messed up some math. You know, if you're doing it on a quiz, we didn't on this, but I'm saying maybe if you're doing it on a quiz or an exam, at least you can say, I feel okay with that number. It's reasonable, right? So everything that we've done up until now has mostly been focusing on on acids, right? So what I want to touch on is really quickly on weak bases. We've already done strong bases. Really not much is different when talking about weak acids or talking about weak bases. We just got to make sure we're being diligent, you know, when we set up, what does our reaction look like? Well, it's going to look a little bit different, right? I have my base with water, right? We're not forming hydronium, but instead we're protonating that base. It's abstracting that proton from the water. Therefore, it's making hydroxide. And so just like when we had Ka, we can also write out the base dissociation constant Kb. And it looks almost identical to what we were looking at with Ka, right? It's always product over reactants. But again, the difference is we have hydroxide here in the products. We have our protonated base in the products, and everything divided by the original concentration, or sorry, not the original concentration, just the concentration of the non-protonated base. So what I have below that is a real example, and a common example is ammonia. So we have NH3, that's our base. It will extract a hydrogen from the water. So one H goes over to there. That's been protonated to form ammonium. And because it lost that H, I have my hydroxide. I write out my Ka expression, my products, ammonium and hydroxide, divided by my non-protonated base. So not much difference. The big thing that trips people up is almost getting stuck in patterns and not recognizing like, oh, maybe I'm looking at a base now. Similar processes in solving problems, but I need to pay attention to using Kb instead of Ka, or maybe I give you Ka and you got to solve for Kb. We're going to get to that in a second. So why don't we do a quick example problem using Kb, and we're going to see it's going through very similar steps. So it's asking us to calculate the pH of a 0.10 molar solution of ammonia, and it gave me the Kb for ammonia. And so I can write out the balanced chemical reaction. Again, set up my ice table, my initial, my change, and then my equilibrium concentrations. I have a Kb. I can substitute in my E, all the values in my E row, plug in my numbers. I can make my assumption. Again, I'm asking, stating that X is much, much smaller, much, much smaller than, what am I comparing it to? The number 0.10. I can solve for X, check my assumption. Oops, I guess I didn't do it out by, write it out, so we'll do it out by hand. Again, we can check our assumption because we're saying that's our assumption. If I take this 0.10 and I subtract 0.0013, we'll do that out. So 0.1 minus 0.0013, I have now 0.0987. Check where my significant figures are. 8 will then round up that 9. Sorry, it's a funky looking 9, but it's a 9. And it rounds me to 0.10. My assumption holds because that was my assumption. At least my assumption, instead of writing it out like I did up here, the equation that I have down here, both are saying the same thing. So my assumption holds. I can then go back, take a look at what does X represent, right? Before, when we were just dealing with acids, it was pretty easy. You take X, like, okay, I know X is equal to hydronium concentration, take the negative log of the number, be done, right? This is where I'm saying don't get stuck into patterns. Recognize what X actually represents. It's the concentration of ammonium and hydroxide. So I now have a concentration for hydroxide is 1.3 times 10 to the negative third. I cannot dump it directly into the pH equation because that's not going to, remember, if we look at that, I'll write it down again, right? It's specifically the negative log of hydronium, not hydroxide. So we're going to have two options on how to convert the concentration of hydroxide into hydronium. So I'm going to show you two ways. One is we can just directly use the Kw expression. So everything I said for this chapter will be at 25 degrees. So I know Kw is not changing. I just solved for the concentration of hydroxide. So I can plug in and find the concentration of hydronium. Do that out. I'll get 7.5 times 10 to the negative 12th. And then I can immediately just plug it into my pH equation. I get a pH of 11.11. Does that make sense? Yeah, it does. I was dealing with a base. My pH should be greater than 7 because it's basic. Do I have the correct amount of sig figs? I do. I have two significant figures, so I'm in good shape. Let me see if I forget if I have these on the slide or not. Oh, let me show you how to do the quick way. Not a quick way, maybe it's just another alternative way. So instead of going through the step of going from Kw, using Kw to get the concentration of hydronium and then taking the next step to get the pH, another alternative is to apply the negative log to this entire equation. So what is that? That's supposed to say log, but what would that look like, right? So negative log. This would turn the equation into pKw equals pH plus POH equals, and if you take the negative log of 10 to the negative 14th, you get 14. So what I could do is going to be taking the negative log of 1.3 times 10 to the negative third. That will get me POH. So if I plug that into my calculator, I will get a POH equal to 2.89. That's not what the question was asking. It's asking for pH, so I can say pH, and I'm rearranging this equation up here, is 14 minus POH, and then I'll get the same number. So 14 minus 2.89. And again, I get 11.11. So two ways, it's technically using the same equation. It's just one, two different ways to approach it. Technically, it is using the same equation. It's just a little bit different. So I just wanted to show you both ways. Let me get through these slides. We just saw these. All right, so this will be the last section on this video. And what this will be doing is comparing Kb to Ka, right? So we've already discussed Bronsted-Lowry acids and bases and that they come in conjugate acid-base pairs. So if we take ammonia, for example, right, they're going to be in conjugate acid-base pairs. Why? Well, if I took my ammonia and it reacts with water, it would then, because ammonia is the base, it's going to take a proton from the water, right, leaving behind ammonium and hydroxide. If I went through and if I asked you the question, what if this is the Bronsted-Lowry base and this is my Bronsted-Lowry acid? Well, ammonia is going to be the conjugate acid, and that's exactly what we see up here. There's my base, there's my conjugate acid. And so actually there's going to be a Kb expression for ammonia. And you can also go through and write a Ka expression for ammonium and actually determine the Ka value for the conjugate acid and also the Kb value for the base. So it sounds a little confusing. It might be right now, but let me show you an example of actually how Kb and Ka are related. So they look very different, but they're actually related. So let's take an example and we'll go kind of slowly through it. So on the previous slide, I wrote out the balanced chemical reaction for ammonia acting as a base, right? So you can also write out its conjugate acid ammonium as a Ka, right? So now I actually have a Ka expression for ammonium, a Kb expression for ammonia. Let's see what happens if we treat this like a Hess's law problem. If I add the two equations together. So I'm going to cancel out things that appear on both sides. So if I take a look here, well, ammonium and ammonium both appear on the same side, so they get canceled. Ammonia and ammonia both appear on opposite sides, so they get canceled. And then when I look at nothing else cancels out, I add the two together, and this equation looks really familiar. Two molecules of water, pure water, interacting with each other to make hydronium and hydroxide. Well, that's Kw. So we're actually seeing there's a relationship between Ka and Kw. Even though we added these two equations together, because of log rules, the way things are related, it's actually Ka times Kb. And so this is just coming from algebraic rules. So again, we can also see why Ka times Kb will give us Kw. So if I set it up Ka times Kb, what do I see? Ammonium and ammonium cancel, ammonia and ammonia cancel, and guess what's left over? My Kw expression. So when you have only when you have a conjugate acid-base pair, it's not any acid and any base, it has to be a conjugate acid-base pair, Ka times Kb equals Kw. And you can prove it to yourself there. I just grab both of those values off the last table, you multiply them together, and you'll get the value for Kw. So all I have on this slide is just kind of a summary of the equation. So I'll give you both. You'll have this equation. You can also apply multiply everything by p or the negative log. In that case, again, log rules. What might be confusing again, when you apply logs to multiplication, they become addition. So that's why when it's written without p, you see Ka times Kb. When you have applied the p, it's Ka plus Kb equals pKw. So whichever you're more comfortable with, you're more than welcome to use. So this will be the last part of the lecture. It's just, again, setting up an ice table, but now using that Ka-Kb expression. So it's saying calculate the pH of a 0.4 molar solution of ammonia at 25 degrees Celsius. The thing is, right, this is where it comes down to critical thinking and paying attention. The question gives me the Ka for ammonium, which is the conjugate acid of the base, ammonia. So this is where we don't want to get ourselves confused. I have ammonia. So I start with what I'm given. I write out ammonia dissolving into water. It's going to react with water. Ammonia is the base, creating ammonium and hydroxide. So don't let that Ka trip you up too much. Set up my ice table like normal. The only thing now is I can't directly use the Ka because Ka is meant for the conjugate acid. So I'll have to do one additional step, convert Ka of the conjugate acid back into Kb for the base, which is going to be ammonia. And that's what I have down here. Sorry, that's my alarm going off. So then I can solve for Kb. Now that I have my Kb, 1.8 times 10 to the negative fifth, I can go ahead and solve the ice table like normal. So there's my Kb expression. Plug everything in, make my assumptions, check my assumptions. My assumption holds. So I'm just trying to go quick. You guys can go through this on your own. I don't want to waste too much of your time, but we're seeing, so I solve for X, recognize that again, stop, ask yourself the question, what does X represent, right? It represents the concentration of hydroxide. I was asked for pH, so I have to convert concentration hydroxide to concentration hydronium, and that's what we have here. Then I can plug that into my pH equation, and then I get my pH of 11.43. Stop, ask yourself, does that make sense? It does. I have a weak base, right? So my pH should be above 7 for a basic solution, and 11.43 is. And it's, it's fairly strong-ish as a base, but it's definitely not strong at all. Like a strong base would be like pH 14 or like 13, right? We're, 11. So we're weak base, and that makes sense. All right, so that will end today's lecture. So please take today or tomorrow, even Wednesday, go over these, lecture slides, take notes, do some of the problems out. And then we're going to pick up after this, still following the syllabus. All right, so I hope everyone's staying safe, and I will see you all on Wednesday.